Okay, then let's start with the next component of this course. The next component is, although like the bigger category is power system, but you would see still the concepts which you have learned either in this course or previous course sort of touching upon. It's not that we are going to do completely different now. It's still the same. You would see still whatever we have learned gets applied. Whatever you have learned in the previous course 114 gets applied. Whatever you have learned in machines lab gets applied. But as a broader category, we are going to look more towards power systems now, right? What is the basic difference? The power systems means the whole system, the whole grid, which includes how the power gets generated, how the power gets transmitted, how the power gets distributed, and how does it get absorbed, right? What we are looking at so far is power electronics, which is more focused, narrowed down to the power conversion or the power processing part of it, right? Now we are looking at a little higher level, that is at system level. The interesting part is that, whichever course I try to teach, it sort of starts from late 1800s, right? Whether I try to talk about history of electric vehicles, whether I try to talk about history of motors, whether I try to talk about history of power electronics, or if I try to talk about history of power systems, right? Everything sort of roughly starts late 1900s. So, Edison, all of us know, right? Edison was more of an inventor, I would say, and he of course had his own company where he was converting some of his inventions into commercial products. So, this was one of the early installations of a power system, so to say. What they did is, so there was a generator, right? This was a DC generator. So, the same DC motor, right, which we have studied in the first course, the same motor can be used as a generator if you have a prime mover, right? So, it was a DC generator which was powering a street which had these light bulbs, right? It was a 110 volt DC getting distributed across multiple bulbs. Some say it started with about 400 bulbs and then eventually it expanded to about 10,000 bulbs or so on, right? Each bulb of about 80 watt, which is a typical incandescent bulb, right? It used to be there. So, one generator and multiple loads, right? And so, it's not really a power system, because the power system today is much more complex and much more networked, right? You have multiple generators connected through multiple transmission lines and then feeding multiple types and loads spread across the whole country, right? Like hundreds or thousands of kilometers away. But yeah, so this was of course a much smaller system, only one generator feeding multiple loads again in the vicinity. Everything was nearby, because 110 volt, as you understand, you cannot really take it very far away, right? Even if you try to take 110 volt, you are generating, let's say in this building, and you try to take it to electrical engineering department or maybe to hostel, for example, right? You would see that if you start drawing more power, there are substantial voltage drops. And you may not get 110 there, you may get 100, 90, whatever, 85, it may not be good. So, this was a small system, a DC system, right? This is one of the early one. Of course, this is what I could find online. There were similar things going on at that time in Europe also, right? In Britain also, somebody would have done a small DC demonstration and so on. But this is one I found, so this was in New York city. There was, I think, one street, I forgot the name, where this installation was done. Similarly, there were around the same time, there were people doing some AC installations also. Same characteristics, in a sense that you will have one generator and then you would feed the load. So, this is somewhere in Britain. This is place near London called Deptford. It had about 10,000 horsepower generation. 10,000 horsepower, this was a much bigger system than the previous one. 10,000 horsepower means how much? 10,000 horsepower is how much? Kilowatt, megawatt, gigawatt? 746, about 7 megawatt. Is that right? 10,000 horsepower is how much megawatt? Yeah, about 7.5 megawatt, right? Yeah. This was of course an AC generation system. Again, one of the initial ones which powered parts of the city of London. So, this was one of the initial AC installation. This was Okay, so the previous one was around 1880, in the beginning of 1880. This was around beginning of 1890, right? So maybe let's say 10 years away. But this is the period when, as we understand, there was a big debate going on between AC and DC system, and these are the few people who were involved. So the black and white picture on the left is what? Who? That is Edison, right? The black and white picture next to Edison is who? Sorry? No, not horrible name. I don't know what do you call horrible. Definitely not horrible name. Normal name. Any guess? Okay. Okay. Maybe forget about that. Let's go to the other picture. Huh? So this other picture, left side is Thomas Edison. The right side is Nikola Tesla. Right. So now the question is, do you want to compare these two? Because Edison is more of an inventor and he has his own company, he's commercializing things which he's inventing and so on, right? Tesla on the other hand is more of a scientist, right? So he's just, for the fun of finding things, he's finding it. Probably he's not very keen on commercializing it, he's not very keen on directly, earning a lot of money or fame out of there. This guy's name is Westinghouse, George Westinghouse, right? So Westinghouse was again a big company at that time, and essentially it was a big competition to Edison's company. So Westinghouse, I don't think he himself was a big scientist or something, but he felt that AC distribution system or AC system is much more powerful. So he bought or he took patents from other scientists and started building those systems. So I think he took patent from Stanley for transformer. He took patent from Tesla on induction machine. So Westinghouse on the left is more of a promoter of AC, and Edison on the right is more of a promoter of DC. So a lot of things, I think in that 10-15 years, a lot of things happened. One of the funny thing happened is that initially when AC was there, to create or rather to sort of project that how unsafe an AC could be, there were things like, there was something, I don't know if it's true or not, but this is what I read, that there was like electric chair for execute, let's say, people, right? So that prototype was powered by AC to sort of connect your mind that look, AC is equals to, very dangerous, something very dangerous. So people, yeah, of course would have got a little bit afraid. Of course, initially any system you set up, right, there are going to be failures. So EVs came, there were few EVs catching fire and so on. At that time also AC system would have got established, there would have been accidents and such kind of things may have happened. So overall it did create a bit of negative sort of feeling around AC, but eventually it was technically much more viable because of the inventions of transformer and induction motor. Right, induction motor, as you now realize that it's like a household thing, right? Everywhere you have induction motors, runs on AC, and then transformers, because if you want to generate power at a little away distance, then you cannot transmit 110 volt DC, right? You cannot transmit it over a city or something. But you can do it if you can do it for using a transformer. If you have a low voltage AC, you can step it up and then you can transfer over a longer distance, right? Much longer distances. So therefore, overall, after that, it did came out that AC is better. So I think towards the end of 1900s, right? Towards the end of 1800s, sorry, towards the end of 1800s, 1890s, 1895, it was sort of accepted that AC is going to be the predominant system of electricity generation and electricity consumption. Good thing was that the incandescent bulb would have worked with both, right, with AC as well as DC. So that part sort of didn't bother much. From that point, let's say for next 10-15 years, right, so 1900 or 1890 to 1910, every major city in, let's say, some of the developed countries started having these electrical loads, and there was a power generation system very nearby to that city, which would produce an AC voltage. Maybe you step it up a little bit or you directly transmit it, then you step it down and you use it for loads, right? You go to houses, go to industries and so on. Of course, earlier everything was mechanical load, right? So horse would go around, and then in circle, and then water would sort of come up. Now you can replace it with an induction motor, right? An induction motor can pull water out. So this transformation was happening, and most of the cities required power which was getting generated in a relatively nearby. Relatively nearby means that, let's say, around 5 kilometers, 7 kilometers or so on. This was growing in those 20 years, but there were a couple of problems with that approach. One problem was, hypothetically, let's say you are in a city and then you have one generator. What if the generator fails, right? Generator can fail, and if generator fails, you are out of power, right? So there was, if you have one generator, then there are few challenges. First of them is reliability, right? The second is let's say this hypothetical plot of load power versus time of the day. So this is, let's assume, late evening or night. This is of course late night, again power requirement goes down, and maybe this is morning and so on, right. So if you consider any load, you consider load in campus, anywhere, any small region, any city, load will fluctuate, right. The load requirement will fluctuate throughout the day, it will keep varying. Let's just put some number, let's say this is the minimum point and this is about some random number, let's say 1 megawatt or 1 MVA, so to say, right, and this is the maximum point, let's say this is appears to be 2 times 2 MVA. Now if you have this kind of a load profile, and if you have only one generator feeding that load, right, what should be the power rating of that generator to feed this kind of a load? What should be the rated power of that generator? 2 MVA or maybe more than that. You may probably, this is again maybe averaged over one day. The worst case, if all the loads, which to be, there is some special day, special occasion, everybody turns on all the lights and whatever, right. So this may go higher also. So probably let's say you may have a generator of 2.5 MVA or let's say 3 MVA, just to be on the safer side. Right. Now you have this 3 MVA generator for your city, but that's not actually producing 3 MVA ever, right. So you could have, if you had some way of having this variable capacity, you could have had much lesser in the nights, maybe higher in the evenings, and that too depending on the load. If you can adjust, there is nothing like that. But here you are like installing a much bigger system. So in a way you are oversizing, over capacity of the generator. Right? This is sort of a second problem. So although you don't really need that much, but to take care of the sort of contingencies or take care of uncertainties in the load requirement, take care of the load changing over the day, you have to install a bigger generator. So if each city does it, everyone has to install a bigger one, right. By the way, this is a typical, more to say, a residential profile, right. If you see industrial load profile, it could be much different. It could be during the day, it could be running at a higher requirement, and night, for example, if the industry doesn't run for night, it may be just quiet, it may be just sitting down, right. The third problem here is that if you have, so for example, consider coal generation, right. If you had a coal generation, so how coal generation works is you burn coal, then that will produce heat, then you boil water, you create steam, and then you use the steam to run a turbine, right. With that pressure, it will sort of make sure the turbine moves. If you are having a 3 MVA generator and you are only running it for a load of 1 MVA or 1 megawatt, right, the efficiencies of the same generator is very poor as compared to running it for 3 MVA or 2.5 MVA. The reason is because there will be always these fixed losses. For example, you make a place to sort of burn coal, right, it will produce heat, some of it will go to the system, some of it will go out, right, it will always go out, whether you are running it at lower speed, higher speed, doesn't really matter, lower power, higher power. Again, boiler will have some insulation, which will maintain the pressure, maintain the temperature, but again, you know, there would be some sort of heat flowing out of it always. So there is always fixed sort of power loss happening in these kind of systems, and therefore they are always much inefficient if you are running it at lower power as compared to if you could run at a higher power. So imagine if this point you had only one MVA generator, if you would have been running that, would have been much more efficient than running a 3 MVA generator to provide 1 megawatt of power, right. The third problem was poor efficiency at light load, right. These were the three basic challenges which were there, but nevertheless, I mean, that time people knew that is the only way out, so people were using it, but I think in the beginning of 1900s, people realized that these are the main problems, and then how do we fix it, right. So how do you fix it? How do you fix it? Time off? Oh, that is probably a little farther ahead, right? Much simpler system, much simpler thing to do. I mean, assume you are in 1900s, right? At this point, most likely the power production, the power distribution, everything is handled by like one company, and you are in your city with one company. You don't know what other people are doing. Yeah. Yeah. Correct. Yeah. So that you can do, right? You can have multiple generators instead of having one 3 MVA. You have 3 units of 1 MVA, right? And then you turn on one of them, keep the other one off, turn on the other one, keep them off, turn on the third one. This could be one approach. There are still some challenges to turn on the generator. It's not that you just plug it in, turn the button, it will turn on, right? You can understand or you can imagine you have to burn coal, right, which would take some time to sort of start the flame, build appropriate heat, and then that heat would convert water into steam with sufficient pressure. It will take some time to turn on. It's not an instantaneous process, right? So yes, you can do it and you can do sort of some amount of stepping up and so on, but an even better system is if you have a residential sort of society or a residential area or a city, you have an industrial city, you have multiple cities, if you can connect them together, right, then what you can do is you can probably remove some of these sort of uncertainties, or at least you cannot remove, but you can minimize these uncertainties, right. And that way, if you connect all the system together, you can keep some generators off. So let's say this 3 MVA, I will keep it off. In the morning time, I can feed this city and the next city using a common generator. I can keep doing that. In the evening, I can probably turn on this generator also, keep the third one on only if required kind of basis. So if you connect these cities together, right, through a network of transmission and distribution line, that sort of solves these three problems. Increases reliability because your generator fails, no problem, you can get power from the other one, right. You don't necessarily have to oversize significantly for your city because there may be other loads who are more here, less here, so they may compensate for it. You don't have to oversize that much. And again, you can shut down some generators if you are not in use, as long as you can predict and you can start them a little bit before the actual requirement. So the efficiency also in general goes up, may not be really high, but it certainly goes up as compared to this scenario, right. So these three problems are in a way people felt could be solved by interconnecting multiple generator and load systems, right. Yeah. Oh, I have no idea. Maybe electrocution is what I guessed. Electrocution, right? Yeah, yeah. Yes. So I think, yeah, so there are these stories, I don't know at least if it's true or not, but yeah. So there were like demonstrations shown with animals and so on, which showed that, AC is much more dangerous than DC, because if you give AC to some living being, then it gets electrocuted, right? Yeah. So this way, from 1930s or so on, people got aware that there is a lot of advantage of connecting infrastructure together. In 1926, there is something called as Central Electricity Board, which got set up in Britain. It started interconnecting about 500 different generators, right, spread across multiple cities. Of course, slowly, because finally it would require a lot of money to connect these cities through some transmission infrastructure, right. So you can connect nearby cities first, and then slowly try to connect other cities and so on, right. Let me talk a little bit about the Indian sort of grid system. I think so if you go and if you do a Wikipedia search, you would realize that there was electricity generation was there long back, even before 1950s. There was one of the local electric train which was running and so on. But the main sort of thing that happened is around 1990s. So this is a map somewhere around 2010, by the way. This is not a recent map, not a very old map also. It shows some power lines or transmission lines which are there throughout the country. But predominantly till 1990s, right, we had not very small grids, but we had like 5 major grids, right. So there was a northern grid, there was a southern grid, there was a western grid, there was a eastern grid, and there was a northeastern grid, right. So we had these 5. So there is of course a benefit of connecting these generators together, right. So around 1990s we had these 5 major grids, and from there, that point onwards, we started interconnecting even these major grids one by one, right. There's a timeline, there's a sequence, because there's always an advantage of interconnecting more grid, right, which we now realize. If you see north part, right, for example, or northeastern part may have substantial hydro, right. The southern part may not have hydro. Southern part had lot of wind, right. Uh, Other parts may not have so much of wind. If you talk about today's context, then there is a lot of solar in Rajasthan and Maharashtra and MP probably, right. Other parts may not have it. And not just load, these sources also have their characteristics. Different time of the day, they will have different power, right. Solar will have more power during the day, wind can have different characteristics. So it's always good to sort of, keep connecting and so that anytime this guy needs power, there's excess power there, you can give it, right. So always these interconnections help. Of course, they cost you. So over a period of time, they get built. So 31st of December 2013, right, is when all these 5 zones were connected together. The last one to connect was the southern part with the rest of the country, right. That was the last connection through synchronous link, right. What do you mean by synchronous link? Synchronous link means AC transmission. You can always connect 2 grids using HVDC. We talked about HVDC right in the beginning of this course. You can always have 2 grids, you can connect them, have a rectifier, pass on the AC power, HVDC, and then have an inverter, right. There still you can make sure the power flows from one grid to another grid. But that is asynchronous. We call it asynchronous. Why? Because the frequencies on both sides need not be synchronized. But what I am saying is that 2013 December is the whole country got connected through synchronous link. That means anywhere you go at steady state, you would see the same frequency, right. So the sort of the catchphrase was one nation, one grid, one frequency, right. So anywhere you go, you plug, you would have the same frequency. Of course, there were still HVDC lines there, but they were also in parallel, there was a synchronous line, so that both the ends frequencies are the same. If you see, as of now, our grid is also connected to or rather we also exchange power with some of the neighboring countries, including Nepal, Bangladesh, Myanmar and Bhutan, right. These are the 4 countries with which we exchange power as of today. Bhutan, we on a net we import power from Bhutan. My guess is Bhutan would have a reasonably good hydro capacity and so on. So we do import net power from Bhutan. For all the rest of the 3 countries, we export power, right. With Bhutan, with Myanmar, we have a very small connection which is about 3 megawatt. Just to give you a context of how much is 3 megawatt, how much is 3 megawatt? No, not one hostel. If you see one house, right, a typical house would, let's say, be about 10 kilowatt or 10 kVA. So, 3 megawatt means how many houses? How many houses? 3000 divided by 10. It's about 300, right? Yeah. So, 300, yeah, would not be much. It could be a big residential society, so to say. I hope you are doing the math correct. Yeah, 5 to 10 kilowatt is a typical house, right? And is the typical connection to a house, 5 kilowatt or so. So, maybe 600 houses, maybe 1000 houses, right? So, 3 megawatt is a very, very small link. I think the IIT capacity would be much more than 3 megawatt also. But anyways, this is the data I found. But with Nepal, I think the data appears to be more accurate. It's about 1.2 gigawatt link, with Bangladesh 1.16 gigawatt link, and with Bhutan about 2 gigawatt link, right? With Bhutan, we have a synchronous connection. That means we have an AC line connecting the two sort of power grids, right? With other countries, we have again HVDC kind of connections which are not synchronous lines. I have to check the value for Myanmar because 3 megawatt does appear to be really, really low. So, I need to check that. Anyways, in terms of the grid, as of today, if you see in the world, which country has the biggest power grid? China, right? China has the biggest power grid, which is roughly about 5 times our system, right? In terms of the installed capacity, in terms of the complete installed capacity, China is 5 times. Which is the second one? US is the second one, right? US is about 2.5 times our capacity, right? Third is India. After India, it's Russia, Japan, maybe I don't remember the exact ordering, but they are around, let's say, 0.7 times of our capacity, right? And then followed by a lot of other countries. This is country wise, not continent wise. So China, US, and then followed by India, and then I think maybe Japan, and then Russia, or other way around. Yeah. So, if you see any new plant you build, right, they may be also connected by a high voltage DC transmission also, but there is very likely scenario that they are connected through the synchronous link. The case I know of is something called as an offshore wind generation, especially in Europe, right? There is huge wind, Denmark and all. So, you would have a wind farm or a wind plant situated completely off the land, right, in the sea. And now from there, bringing power in terms of DC makes much more sense. So, it makes sense not to have any synchronous link because anyways there are no loads there. It's only pure generation. So, you can have an DC link connecting that offshore farm with the mainland, right? But as far as my understanding is there, in India, all the generation, all the loads are connected through synchronous link. There may be parallelly asynchronous links or high voltage DC transmission happening as well. Is it? Oh, okay. Makes sense. Maybe which has about 600 houses, maybe 1000 houses that you can search now. Okay. Okay, let's look at some of the statistics of what constitutes India's power generation, right? So, total this value keeps on growing up. Of course, every month you see this grows up because there's more and more installed capacity. All of you understand the word installed capacity, right? Installed capacity means this is the total gigawatt or megawatt of electricity theoretically we can produce at the same time. Why I say theoretically? Because in practice you can never produce all the generators running at the full capacity at the same instant, right? So, this is like the maximum we can produce power at any instant of time. This is the installed capacity, right. So, it's about 466 gigawatt as of January 2025. You can go to CEA, CEA stands for Central Electricity Authority, and you will get all the data there, right, the first hand data. You don't have to use a second sort of data from some other sources. So, this is a table, this is a data picked up from there. Thermal, if you see, constitutes major part, about 213 gigawatt of coal, right, followed by lignite, which is actually a coal which is more of a locally available coal which has lesser calorific value, and then you have some gas generation, not much in India, but there is some amount of gas. Some of the other countries have much more gas generation than India. India is predominantly coal. Then there are very few diesel. Diesel is mostly like where there is no grid or very remote areas, but again not much diesel. So predominantly if you see in India we have thermal, which includes all the three categories, and then we have nuclear, somewhat renewable. Renewable is split into two major categories. One is this big hydro, right, which is about 46 gigawatt, quite substantial, and then the other renewable which includes solar and wind predominantly, and there are maybe few biogas and so on sort of plants, also very small ones, right. But the whole renewable, if you add the hydro and the other renewables, is about how much? 200, right. So 200 gigawatt about renewable and about maybe 250 gigawatt of thermal, right, or fossil fuel based, so to say. Total about 466 gigawatt. Is that okay? Okay, that I have a slide on that, so I'll show you. What is the? Yeah, so the first level solution is you interconnect. Yeah, that's what I'm saying. The first level solution is you interconnect. That makes it simpler because the uncertainties, let's say, my house, if you give me one generator, when I turn on the switch, it is full power, turn off the switch, is zero power. If you connect 10 houses, it becomes more average. If you connect 1000, it becomes even better. So, one thing is to interconnect. That is the first basic thing to sort of avoid that uncertainty, right? And then yes, now you have day of the time tariff also, which is there. Now there are so many other mechanisms which are a bit more advanced. We will not probably talk about in this course, but later on you can study. But the basic thing is just to connect together, right? That will just make sure that the uncertainties or the sort of noises would become lesser, right? And you would operate more at the mean value. Yes. Morning again it may pick up depending on season and so on, right? If it's a winter season, maybe for the heating load would come up and so on. But yeah, generally night is the predominant load. No, we are not only synchronizing all the residential, we are synchronizing every type of load. We are connecting every type of load, industries, residential, some residential which are in colder region, some residents which are in warmer region. We are just connecting everything together. Average would become lesser and lesser, delta would become smaller and smaller, right, as you keep adding more diversity in terms of your load, right. I think so. I think, yeah, of course. I personally don't work in power systems, but I'm sure colleagues in power system would work with some of the. I'll tell you what are the different types of companies that exist which are involved here. There's a slide on that also, right? Okay. This is a chart which tells us or answers the other question, which is that what is the growth. So, yeah, not the most appropriate chart, but the y-axis is megawatt installed capacity. So, you remove 3 zeros, you would get gigawatt. The first is, so the different bars essentially shows you the installed capacity for different years. It's not more of a bar, it's more of a trend. So, just try to imagine the top part of the bar getting connected. So, if you see thermal over the last 10 years, 17 to 25, roughly 10 years, 8 years, thermal has grown a bit. Thermal gas has not grown, right. As I told you, we don't use much gas for power generation. I think some of the other countries use quite a bit of gas. Diesel is anyway small, you cannot even see it. Hydro, again, the big hydros, it does appear that it is good to add because they are in a way renewable, but the big hydro projects requires a lot of investment, right, because you have to make a big space dam, you have to have big generators and so on. And secondly, people do talk about some sort of ecological impacts of building these big dams, right, you would see in news and so on. So big hydros are again, more or less steady. Wind power little bit growing, these are small, and then solar is the one which is substantially going up, right. You can see in last 7-8 years it has probably grown from negligible to how much now, about 100 gigawatt plus, right, more than 100 gigawatt, and this is the total growth. So this is again somewhere about 320 gigawatt to 450, 460, 470 gigawatt as of today, right. Yeah, so our total installed capacity is growing much more rapidly, and quite a bit of it is getting contributed by the solar. Does it answer your question? Good. Anyone, why is it that predominantly solar is the one which is growing fastest? Yeah, correct. So he says it's much cheaper. It's in a way it's more affordable in every sense. The per unit price for electricity is less. You can install 1 panel, 2 panel, 5 panel, 5,000 panel, 10,000 panel, right. There is an economy of scale, but more or less it is relatively cheaper as well, even if you install a smaller system, which was not possible with hydro or thermal, right. You cannot have a 1 kilowatt system at your home and have a steam based generation, but you can have it with solar, little bit more price, but still proportional to the prices one would install a megawatt, right. Yes. So over the period of time it is becoming cheaper also. There is no mechanical parts, requires lesser maintenance, doesn't cause any pollution, doesn't require a continuous supply of fuel which is coal. So it does make a lot of sense to install more and more solar. There are associated challenges which we will see a little bit later. Next you see, this is just the data, so you don't have to see it. Yeah, this chart I have taken as it is from CEA website. This again shows you the trend of how different installed capacities are going. So there is wind, small hydro and solar, right. Let's say if you only look at solar, this has of course grown considerably. This goes up to which year? This goes up to 2023. This says about 66 megawatt, but then I have to check because the previous guide showed us 100 megawatt, right. I have to cross check this data and the value in the previous data, but it's a substantial growth. Now this is one part which I want to also highlight, which is, so everything is not so nice about having or whether solar generation, right. So this one tells you installed capacity and another metric which you can use, which is the generation, right. How much of electricity or how much of electrical power or energy is getting generated, right. So the first installed capacity is the power, right, megawatt. The second thing which is the generation is megawatt hour or gigawatt hour, that means the energy output, right. One is the installed capacity power, second is the energy output. So now if you see a thermal plant, right, a coal plant, as long as you have coal, you can run it 24/7, right. You can keep running it, of course you have to shut it down if there is a maintenance schedule, but other than that you can keep running it 24 hours, right, as long as you have coal. But the renewable sources, especially solar, you cannot keep running it for 24 hours, right. You would only run it, it would naturally only run it for a few hours in a day when there is sun, otherwise it would just shut down, it cannot produce power. And therefore, even in the installed capacity, the coal is about 43%, and then you see the renewable plus hydro is about 10%, renewable is about 25%, but the same percentage distribution in terms of the energy produced becomes different. Coal produces about 64% of the energy that we consume, right. Renewable, if you combine hydro and renewable, produces about 20% of the energy that we consume, right. So, even though the installed capacity percentage appears to be much better, but if you see in terms of the energy production, yeah, it's still growing. I mean, it's still on a positive ramp rate, but then as of now, the values are still lesser than what we do through coal. Is that okay? Any doubt? Sorry? Non-utilities may be, small generations, diesel and other things which are distributed, may not necessarily be connected also. Those kind of miscellaneous things is probably what falls under non-utilities, right? Utilities means generally grid connected, right? What do you think? How much coal do we have? Or, we are heavily dependent on coal-based power generation, right? So, how much of the coal that we use for power generation we have locally available?
Only very high percentage because pure of the coal, like a high energy density.
Yeah, we import enormous amount of coal. I'm not very sure because it's something which I read little bit earlier. But we are probably either the world's top or the second top country to in terms of the coal import, right? So, we heavily import coal, we heavily depend on coal that we are importing, right? And that's another problem with coal. One is of course the pollution, the other one is that we have to import it and it has to be a continuous supply. You can store, yes you can store, but still it has to be a continuous supply for you to keep running power generation, as well as lot of other industries which directly use coal to burn it and produce heat. For example, steel industries uses coal, right? A lot of other industries uses coal because you just burn it, you get the heat, you use it for whatever you want to do, right? You want to boil something, you want to heat something, directly heat it using that. So, now there is a lot of emphasis on, for example, steel manufacturing predominantly coal, right? A lot of emphasis on green steel. What is the meaning of green steel? You don't use coal to produce the steel, right? So, substitute coal with some other form of energy. Maybe you have solar panels, produce electricity, use that electricity in your manufacturing process for heating and other things, substitute coal, right? That's the term becoming popular now. So anyway, so this is, anyways, it's a trend that's how it is moving. So, coal is growing very slightly now. I think solar is picking up. Hopefully, in future, solar and other renewables would pick up much faster. This is roughly the ownership of the Indian power sector or the utility or the grid as a whole, right? These are the different players who are involved. It's not like, it's not a one company thing which is doing everything, right, left to right. There are different companies, they work together, and this is roughly what those companies are, what those companies look like, right. So, if you see three major parts, right, generation, transmission and distribution. Generation is done, so majority of the thermal, if you see, it's NTPC plants, right, again spread across the country. Any region you would be there, you would have heard of a nearby NTPC plant, right. So, that is predominantly coal, predominantly thermal, and then NHPC predominantly hydro generation, and now lot of private players as well, especially in renewable generation, right. So, I think in solar you would have heard of I think Adani is certainly there is lot of other companies which are there in solar power generation and so on. So, lot of private players with smaller capacity in renewables as well. Once the power is produced, to transmit it, right, it has to be a little bit sort of a centrally owned infrastructure. So, that is owned by Power Grid Corporation of India Limited, I think PGCIL, which is mainly responsible for larger power transmission at high voltages from one place to the other place. And then once the power reaches to nearby to the city, then there is this distribution network within the city, right, and that is predominantly done by distribution companies. So, in Mumbai, for example, you have MSEB, right, Maharashtra State Electricity Distribution Company, MEDCL, I think my house gets electricity from there. And there are also private players like Tata and I think Adani and so on, right. So, these are mix of private and public players whose job is to distribute electricity once it reaches a center. The fourth bullet is sort of not a physical infrastructure, but more of a intellectual or a control infrastructure, so to say, which is the formerly it was called as POSOCO, which standard for Power Systems Operations Company, right. Now I think recently it got renamed to Grid Controller of India. What it does is it essentially manages the power going to the loads, the load scheduling, the load management, how much power should flow from point A to point B. So it's more of a control and management sort of a activity. So this is roughly how different players in the Indian power sectors are. Okay. The other thing is, what are the different voltage levels that exist in India, right? What are the different voltage levels that exist in India? So usually all these big generators, right, if you have seen an NTPC power plant and so on, you would, I mean, their capacity may be in hundreds of megawatt or whatever. The voltages at which they produce is usually 11 kV, 12 kV of this order, right. This is the voltage that comes out of the generator directly, right, and this is not very high, so you cannot use it to transmit or send it over a long period of distance. So these get stepped up to different values ranging from 220 kV to 400 kV to 765 kV, right. These are all kilovolts, so 765,000 volts. You step up using transformer, you do transmission, this is mainly transmission, this is generation. You transmit over a long period of sort of region. Then maybe once it is little closer to city, you step it down to 132 kV or to 66 kV. This is somewhere between transmission and distribution, some call it sub-transmission. And then you step it down further to, let's say, 33 kV or 11 kV, which is distribution. And then further that 33 or 11 kV gets stepped down to 400 volt and goes to the load as 3-phase or as single phase 230 volt supply, right. These are some of the popular voltage levels that exist, and again, it depends, some other countries may have few other voltage levels and so on. So this is not I mean, mostly these are the levels, but yeah, it changes with country to country, but we have these popular voltage levels that exist. There are exceptions. So if you see, even in IIT Bombay, I saw one substation which has a 22 kV rating. So yeah, you can have a 22 kV as well. So I wanted to show you the power network in campus, right. I'm trying to get that diagram. What is this diagram called? This kind of a diagram is called as SLD, stands for single line diagram, right. In reality, there are 3 phases and neutral and whatnot, right. These diagrams just simplify those things, we just draw it as a single line. So there is, I'm trying to get hold of a SLD for campus. Hopefully, if I can get that, I'll show you how the power gets distributed within the campus, what is the incomer voltage, how does it get stepped down, what are the different infrastructures. Let me talk about one concept somewhere here. So let's say you have an 11 kV line that is coming in, and from there you have a step down transformer which is a 3-phase transformer, right, steps it down to 400 volt, and then it goes further ahead and gets consumed in a load. Now this line, this distribution from transformer to load will have some impedance, right. This transformer will also have some impedance, right. Transformer would also have a leakage inductance and the winding resistance, right. Moreover, this 11 kV, which is supposed to be 11 kV, may not exactly be 11 kV all the time, right, because if your nearby building or nearby society draw more load, then that would also fluctuate or create oscillations or create variations in that 11 kV over a period of time. So therefore, this may not be accurate, there are these voltage drops. So therefore, if the current is drawn by the load, these voltages may also reduce or change the voltages that appears at the load point, right? And these kind of questions you have solved in 114, the previous course. The question is, what do you do? Because if your load doesn't receive, fine, 400 volt line to line it's supposed to receive, maybe it is okay if it receives 395, but not good if it receives 300, right? Your loads may not operate as desired, they may fail, they may stop operating and so on. So, and this is a very practical problem, right? Any network would have it because you would always have these finite impedances. Your network would always have impedances. It's not possible not to have impedances. So, this is a very common distribution side problem, right? Especially when you are dealing with the end loads, you want your voltage to be very tightly regulated. So, how do you solve it? How do you solve it? You know what is the problem I am talking about? You want me to repeat? You have loads, you have sources, the source voltage may change, the 11,000 volt which is coming to IIT, let us say, assuming IIT is getting 11,000 volt, may be getting 22,000, that is changing. Your loads are also changing, because of this impedance the current flow is also there, so the voltage drop across the line will also change. So the net voltage that your fan sees or the light sees will change, right? Which is okay, 5% variation may be okay with you, but not beyond that, right? So what do you do to make sure that voltage that you are getting in your fan is always correct? It's always within the 10% or the 5% band you want. What can you do? What are the possibilities? Okay, he's saying connect a variac. Variac you have all seen in the labs, right? All of you remember variac? How many of you remember variac? Raise your hand. Very few of you. Why is it so? Why you don't remember variac? Variac? All of you have used it in the lab, no? You don't remember the thing which had this black colored knob on the top, right? Maybe you remember it with some other name? Auto transformers, right? Yeah. So auto transformers are there. So what you can do is, in this room for example, I can connect an auto transformer. As soon as power comes in there, it will go to an auto transformer. And then I can change the number of taps in the auto transformer by rotating that knob, right? And that would adjust my output voltage as compared to the input voltage. In this case, if this is the input voltage to the room, this is the output voltage. So I can get a higher output voltage as compared to the input voltages, right? Is that okay? So basic principle is, yes, you have to use some form of auto transformer. But now question is that what is economical, what is practical? Not practical, not economical to have it in every room. You can, of course, manually doing it would be really painful, right? There is a thing like we have a clock, there will be like a voltage and everybody goes and tries to keep adjusting it. You can put a small motor, you can connect it to a small microcontroller, you can measure the output voltages, you can write a small code in a microcontroller whenever the voltage is less than so point, you change the motor or turn the stepper motor right by certain angle, and that would be like a small closed loop system which would operate. But again, doing it at a very small level would be highly unpractical thing. So it is done usually at a substation level, right? It's usually done at a substation level. Okay, new word, substation. Let's first describe what is the meaning of substation. What is the meaning of substation? Substation means the place where you have this guy sitting, right? That's what we call it as substation. Substation means wherever you are getting a certain voltages, you are stepping it down, stepping it up, you have some circuit breaker, some overcurrent protection, and then you are passing on the other voltages towards the load side, right? That place is what we call it as substation. So for example, this building, so to say, might have a transformer room or a substation somewhere nearby, right? So what you do is, in this big transformer, right, this is a relatively big transformer, it's stepping down from 11 kV to 400 volt, you do something like this. This is your input which is nominal 11 kV, of course it will not be accurately 11 kV, and then these are different tappings, right, and this is your output 400 volt side which then goes to the load. Right. So, this is the main substation transformer, the same transformer which is stepping it down from 11 kV to 400 volt. So, instead of having one more auto transformer, in the same transformer you create these different tappings. Tappings means there are n turns, so you try to pick one wire from nth turn, try to pick one wire from n minus 1 turn, try to pick one wire from n minus 2, n plus 1, n plus 2, try to pick 5-10 wires, and then instead of having the rotating mechanism, because if you open an auto transformer, right, how does the rotating mechanism work? There is a spring which is always pushing to this coil, right, and that is how contact is made. If you keep using it, right, that spring becomes loose, there is a little bit more maintenance required. So, instead of, you do not require very fine control anyway, so instead of doing that kind of mechanism, here you connect multiple switches, right, and then you can connect to this guy, 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 you can connect to this guy. So, it is doing something similar, of course in a limited range. You do not want to vary the voltage from 0 to 400 volt, right, you just want to do a fine adjustment of plus minus 10% or so. So, now what you do is, if you can measure the load voltage best, if you cannot measure the load voltage, you measure the voltage here, you measure the current, you try to, if you know the approximate impedance, you try to estimate the load voltage, you check if the load voltage is within 400 volt plus minus 5%, if it is more than 5%, you increase the tapping here, you go higher tap, if it is less than 5%, you reduce the tap, right, reduce the term, because this is high voltage number of taps. If you reduce, then the voltage here will increase, right, this is, so if you reduce N1, your voltage at the output will go up. So, depending on that, you can write a small logic, and this would make sure that the voltages are fairly well maintained, irrespective of the fluctuations here, irrespective of the load fluctuations. Yeah, and N2 remains the same, we change N1 so that V2 can increase or decrease. So, we change N1, not N2. What is the difference in? What's the difference in the cost? Oh, no. So, having one auto transformer extra is of course costly. You anyways have a transformer, you build few more extra things, just take out few more taps from the same transformer. Why do you want to have one more auto transformer? So, from auto transformer, including in the main transformer, is of course much cheaper. In the main transformer, you could have had tappings on the high voltage side, or you could have had tappings on the low voltage side. You could have created tappings anywhere, right? We create it on the high voltage side because less current, yeah. So, on the high voltage side, you have lesser current, so it is easier to make and break circuit, right? On the low voltage side, you have much more current. So, therefore, typically these tappings are on the HV side. Do remember it. If I give you reasoning questions, this one of my favorite questions, right? That why there are tappings on HV side. So, this is called as OLTC, which stands for on load tap changer. On-load tap changer, name suggests you are changing the taps. On-load means on the fly, on the load itself you are changing, you are not shutting it down and then changing the tap, right. So, this is called as on-load tap changer. Some places you would have tap changer, they may be mechanical. So, that means there is no closed loop system, there is no processor, no microcontroller measuring the voltage doing that. It could be a manual job that fine, आज के दिन अच्छे चल रहे हैं, output voltage इतना रहता है, चलने दो. You know, these days are bad, let me change one tap. It could be that way, or it could be an automated system where there is an automatic voltage measurement, a microcontroller doing the same action, not as slow as a human being. Maybe it's taking that action 3-4 times a day, not more than that. Actually, you don't want to take too many actions also, because that will deteriorate the life of these connectors, right. So, you don't want to do it very frequently also, but yeah, some places is automated, some places it could be manual, somebody can just change the tap, right. So, on-load tap changers is what is used popularly to maintain the load voltage. Any question? Anything you want to ask here? Okay, let us look at one more concept. So, there are 3 concepts I wanted to cover. Let me cover one more at least today. So, the next concept is I think we have talked about it in the previous course, but let me still just revise that. Okay. So, the other element in the distribution system is the transformer, right. The transformer itself, all the time, just for convenience, we always make it a single phase and show you single phase, right, but in reality it's never single phase, it's always 3 phase. This is a 3 phase transformer which we have seen in the previous course, right. We have even done calculations for it. We have done it in the previous course, right. You remember it? Okay. This particular, you in 3 phase transformer you can have different arrangements. What is this particular arrangement called? Delta star. So, this is delta star transformer. The symbol is delta star. The star point is also earth, either directly or through a resistance or an impedance, and therefore, this is in the symbol, this is how it is shown. That means it's delta star with neutral point earth, delta star with neutral point earth. Okay, this is the symbol. This is also an equivalent circuit. This is a circuit. In reality, it would look like 3 limbs and then coils wound on those 3 limbs, right. This is the symbol, this is the circuit. In reality, you can Google it, you can see how a transformer looks like. You have seen it in the lab also, right, we have shown you last semester. Okay, so the first thing is that when we do delta to star, right, and if I try to plot the phase voltage or the line voltage of this side and the line voltage of this side, right, let us say these are, I use it as small ABC instead of capital. So, small ABC and capital ABC, right. If I draw the phasor diagram of a small VAB and a capital VAB, how would they look like? I will repeat my question and then we will start from the back. You have to answer it. If I have to, you all of you remember phasor diagrams, right? Phasor diagram. So, if you have to draw the phasor representing VAB, and in the same diagram you have to draw the phasor representing VAB, small ab, how would they look like with respect to each other? Would they overlap exactly both in terms of the magnitude and the angle? Would some of them be at a different angle? Would they have different magnitudes or different length of the vectors? Right, that is the question. So, yeah, I think for a change, let us start from there this time. Yeah. P small AB would be 30 degrees lagging. Okay, I am just drawing what you are saying. So, if you are saying this is VAB capital 1, then small is lagging VAB. Is that what you mean? Is that what you mean? Okay, I am not, let us just check. Yeah, we will come to that, but let us just first figure out about the angle. Is the next person, is this correct? In terms of angle, yeah, magnitude we still have to discuss. Huh? What should be leading? The primary or the small AB should be leading? That is what you mean? Next one, leading, small VAB leading, next one, small VAB leading, Pakka, next one, lagging, okay, small VAB lagging, next one, अब कोई leading बोलो फिर आगे वाले 4 लोग leading होंगे. Okay, so if you see, if this is your real, this is your imaginary plane, no, these are just phasors. So if this is your V small AB, right, this V small AB will have the same phase as VAN, right. So this small VAB is nothing but equal in terms of the phase. There is a magnitude difference, we will come to the magnitude difference, but in terms of phase, this is same as VAN, right, and this is VBC, small VBC, which is same as, in terms of angle, which is same as VBN. So this is V capital BN, and therefore capital VAB will be capital VAN minus VBN, and which would be this one. So which one is leading, delta side or star side? Star side voltage is leading the delta side voltage by an angle of 30 degrees. Magnitude wise, of course, there is a turns ratio. In addition to the turns ratio, the star side magnitude would be √3 times more than the delta side magnitude, right. Does it matter if this is 30 degree leading, then this, does it really matter? Does it help us or create some problem? Does it even matter if this is 30 degree leading? You understand the question? This side is 30 degree leading than this side. The line voltage here is 30 degree leading than the line voltage here. So what? Because these are anyways isolated. You would not connect some component which has a line, which has a wire going here and a wire going here. If you do that, then there is a problem, because the phase line voltage here and the line voltage here would be at 30 degrees, right. Usually all the loads would be completely connected here, they would not know what is the voltage here. So in that sense, it would not really matter much if it is a 30 degree phase shift, right, because while sitting here, you do not know what are the voltages at 11 kV in a way, right, you do not care about them too much. Only place where it does matter is, what if you have these 3 transformers and the output of the 3 transformers are then connected in parallel to feed a bigger load, right. Then all 3 of them should be star delta. You cannot do like one delta delta and one star delta, because then there will be a big problem, right. Just looking at one transformer, there is no problem. If you have 2 of them both connected parallel from the input side as well as on the output side, right, just to increase the capacity, then both have to be delta star. You cannot have one delta delta and the other one delta star, right? Then the phases will not match and then you cannot parallel them if they are not of the same phase. Is that okay? Yep. You won't do that. Now, why would you do that? Yeah, you would connect a load on this side, no? Oh, higher power, you mean? So you would, if you are tunneling, if your one is a star delta, the other one also has to be a star delta, or if one is a delta star, the other one also has to be a delta star. Yes, the load is connected on the star part, star star, okay. So there are now few questions, so this is the most popular sort of architecture used in power system, right, delta star. There are other three combinations also possible. You can have delta delta, you can have star star, you can have star delta, right. Those are not popularly used. The popularly used is delta star. So question is why?
I guess is on the load side we want to neutral wire.
Okay.
Because we don't supply phase, we supply phase neutral most like low loads outside of like ACs or large.
Okay.
Single phase, so we want to neutral the load.
Okay.
We will use the star in the load.
Okay.
And in the supply, like, we don't need an extra wire that is also large current, so we'd rather just have like a delta connected thing so that we don't line it.
So, like for everyone's, let me first tell you what he says. So, he is saying that on the load side, right, you do require neutral because some loads may be single phase loads. Moreover, even if you don't require neutral, right, you cannot let the load side voltages be floating with respect to the ground. So, you need to ground something. So, therefore, if you have a star point, even if you don't want a neutral, the star point you can ground or earth, right, so that you are sure that if you touch a phase, you would get 400 volts. So, you can design your gloves, you can design your shoes, you can design the insulators on that well defined 400 volt. If this is not earth, I am standing there, I touch a line, I don't know how much voltage will get applied across me, right. So therefore, you know, load side it makes sense to have a star, right. Then the question is on the source side, on this side, you could have still had a star, right. Why do you want a delta? That's the next question now. Difficult question. Anyone who has answer? Okay, so I am also not very sure, I have not really thought about it, but my sort of very wild guess here would be that first of all, right, if you have, this is something which you are not covered in the course, but if you have a negative sequence component or if you have a third harmonic current that is flowing here, right, let us say you have this A and N goes to a rectifier, there is a third harmonic current which flows there. If you have delta here, right, the third harmonic current circulates and it does not come from the source. So third, ninth, all those harmonics current does not come from the source. So, but if you have star star, then all those currents might also come from the source, and therefore it sort of helps us reduce the unnecessarily current that we are drawing from the source. The other thing again, my guess is that it would have probably some implication on the material required to build this transformer, but that's something I have to check. I am not very sure. So the harmonics I am very sure about, that if you have third harmonic here, you don't have any third harmonic coming from the source, so that way it helps having a delta and a star this way. There may be extra benefits, let me just find out and then I'll update you in the next class. Okay. I will cover this slide next time, but I just wanted to show you this slide because it's like a very recent event which happened. All of you know about this? Coincidentally, 21st March, this happened, and I think just a day before or something, I was traveling internationally. Of course, my transit was not through London, fortunately, it was through Turkey, but never the mind. So I just saw it when I was in India and I realized how big it can be, right. So what happened is there was this, so you see so many news articles, right. So Heathrow Airport, which is the London's like main airport, very busy, very crowded, connects lot of places worldwide, east with west and lot of European destinations. The power to that Heathrow place and the airport got shut down for about I think 24 hours or something like that. The reason was that, and full reason is not disclosed, or I could not at least find it, but the sort of high level reason was that the transformer in the substation which was supplying this region, the step down transformer, the same delta star transformer you are looking at, caught fire, right. And usually these substations would have multiple transformers in parallel, they would never have one transformer. Even if you go to our substation, it will have two transformers, three transformers, right. Why? Because in case of these events, if at all something happens, you can turn off one, right. Of course, if you turn off one, now the other one you may not be able to supply whole power, so you turn off few loads also, right, the loads which are not necessary. For example, you could have still continued to run the airport, maybe you would have cut off some of the residential houses for a few hours, something like that, you can manage, right. But I think one news article said that there were 3 transformers, either 1 or 2 of them were under repair, and then this third one caught fire, and then nothing could be done. It took quite a lot of time to restore the other 2 and then got the power back. There is some value, 78 million USD, I don't know if it makes lot of sense, but there is of course a huge loss which happened because of all flight cancellations, flight diversion and so on. The important thing which comes out from this event is that this transformer, right, which of course we study and it appears to be a very sort of robust and simple thing to have. It's a relatively custom manufacturing, right, especially for these big ones, and it may take substantial time. So if you place an order, it may take something like 6 months to a year to manufacture that transformer, right. All the renewable, all the solar, anything that we are talking about, right, there are a lot of solar panels required, power electronics required, but this transformer is required each and every place, right. So although this is a very important part of infrastructure and it has its own limitation also, it is made up of copper and steel, both the prices are also going up and so on. So it's an important part of infrastructure. There are people who are now doing research on how do you replace this transformer with a power electronic circuit, right, which should be the case, right. You have DC-DC converters, it changes one DC voltage to another DC voltage. Why can't you have AC to AC converter instead of using a transformer which would change one 11 kV voltage to a 400 volt voltage, right. So there are people doing research on that as well. Just one event I wanted to let you know. With this we will stop today's lecture and we will meet next week.